Okay, welcome to the NUPOC video study guide number 72. Let's go ahead and move into some electrical engineering problems, specifically electromagnetics, because it's a really good takeoff on some of the physics that we've been going over. And we'll probably do some circuits and I don't know, maybe digital logic and electrical machines and of course electromagnetics, and all of these things I'll just bundle under the electrical engineering topic, and I'll do the same thing when we get to mechanical engineering and whatnot. We'll just take all those subtopics and just kind of bundle them together. If you do want to look this problem up or look up the solutions in the study guides, it's actually question 1 in the electromagnetics section of guide 1. And basically it's just asking us what's capacitance and inductance, right? So I'm sure most of you, even if you're not electrical engineers, are familiar, at least at a very high level, with capacitors and inductors, right? So if we look at capacitance, okay, we know it has something to do with a capacitor, and capacitance is basically just the ability of a structure like a capacitor, which is just an electrical structure. I mean, physically in its simplest form, it's just two parallel conducting plates like this, these two parallel plates, and it's got some dielectric material between them. Maybe that's just air, right? And then we charge up these plates, so maybe we have some positive charges here and some negative charges here, and the capacitance of the plate, the capacitance of the capacitor, let's say C, right, there's some capacitance value to this, is just the ability of this capacitor to store a certain amount of charge for a given voltage. Right? So capacitance is just charge per volt, right? So the units are coulombs per volt. So sometimes you'll see, like maybe in a textbook, Q equals CV is a fundamental equation for capacitor, right? This is just saying charge equals capacitance times voltage, right? So it's the same thing if we just brought this voltage up to this side of the equation. We'd have the same thing, charge equals capacitance times voltage. Right? So capacitance is just the ability of an electrical structure to store a certain amount of charge per volt. So if we have a very high capacitance, that means that we will store a lot of charge even with a very small voltage applied. And if we have a very small capacitance, it means that we won't store much charge even if we apply a very high voltage, right? And another way to think about this, another point of view to look at capacitance from, is to say that capacitance is the ability of a structure to resist change in voltage, right? And so this kind of perspective, this way of looking at it, comes out of looking at it from the point of view of Ampere's law, actually. Right? So if we look at Ampere's law, which is one of Maxwell's equations, right? So if we A-M-P-E-R, I think there might be like an accent in there, Ampere's law, right? It says that if we integrate, right? If we integrate the vector H field around a closed path, that it's equal to time derivative of the integral over the surface, over any surface terminated on this closed loop, of the electric flux density normal to that surface, right? Now, so we have some loop here. Well, I'm not going to bother drawing it out. I'll just kind of go through how this all works out to say that capacitance is the ability to resist change in voltage, right? So if we take the vector H field, right, and we look at its units, it's in amperes per meter, right? And so we're going to integrate this around a closed loop. So we're going to multiply it by some length, meters. So this is going to end up being in amperes. All right, the units are going to be amperes, right? So this is just current. I'm going to call it I. I'm going to call it I sub C because we're looking at a capacitor. This over here, right, D, the electric flux density, is in coulombs per area, so like coulombs per square meter or something like that. And again, we're going to integrate it over a surface, so we're going to end up with coulombs, right? But we know from this equation, right, that coulombs, or charge, right, equals capacitance times voltage. So this is really just CV here. And of course, we have the time derivative. Now we know that the capacitance, or we're going to assume at least that the capacitance is not changing with time, which means that we have IC equals C, we can pull the C out because it's not changing with time, right, times the time derivative, right, of the voltage on the capacitor, right? So that's if this is IC here and this is VC here, right? So what this means is, right, if the capacitance is very large, right, that it takes a large current just to get a small change in voltage, right? A small dV dt, right? Another way to think about it is if there's a very large capacitance, any small change, just a small change in voltage, will create a very large current, right? So if we have a large capacitor, right, and we try to change its voltage a little bit, it'll resist that with a large current. And if we try to change its voltage by injecting a current, it's going to take a very large current just to create a small change in voltage. And that's if the capacitance is large. Now if the capacitance is small, then it's the opposite, right? It takes a very small current to change the voltage, all right? So now let's kind of look at the dual of this and look at the inductor, right? So the inductor is just another electrical structure, and it's made by, well, there's many ways to make it with different cores and such, but let's just say it's just a coil of wire, right? And every wire has some intrinsic inductance to it and capacitance, and stray inductances and parasitic capacitances and all these things. But let's just talk about, we have some coil of wire and it's just sitting here in air. There's no extra core or anything like that. And similar to the capacitor, right, or similar to capacitance, inductance, right, which we represent with L, is simply flux, magnetic flux per amp. It's actually flux linkage per amp, but we don't have to get too complicated. We don't have to talk about flux linkage and flux. We'll just say it's flux per amp, right? We'll represent that as phi per A, right? So what this means is, if we have a very large inductance, we will generate a lot of flux, right, with just a small current. And if we have a very small inductance, then it will take a large current just to generate a small amount of flux, right? Now, similar to the capacitor, another way to think about this is inductance is the ability of a structure to resist change in current, right? So a capacitor, the capacitance is the ability to resist change in voltage. The inductance is the ability to resist change in current. And again, we can kind of look at this from first principles. So we can actually take a look. I'm going to just draw a line down the middle here. We can take a look at Faraday's law, right? And see how this comes up with one of the fundamental equations of the inductor, and how that shows us that the inductor resists change in current. So Faraday's law will say that if we integrate the vector electric field around a closed loop, that it's equal to the negative time derivative of the integral, surface integral, of the B field over any surface, the surface integral of the B field normal to any surface terminated on this loop that we integrated the electric field around. So if we integrate the electric field, which is of course in volts per meter, and we integrate it over some distance, we'll just get volts, and I'll say that's VL because we're dealing with an inductor, and that's equal to minus the time derivative of this whole thing, and of course the vector B field, right, is in Webers per square meter, right? So it's essentially in flux per square meter, right? It's a magnetic flux density. So if we integrate it over some area, we'll get magnetic flux, right? And we said here that inductance is flux per amp, so that means that flux is inductance times current, let's say I, right? So that means we can say this is the negative time derivative of L times I. I'll put a sub L there to indicate that it's for an inductor. And similar to the capacitor, we assume this inductance is not changing with time. So we bring it out to the front, and we end up with VL equals minus L DIL dt, right? And we have this minus sign floating around in here, and that's just due to the vector convention of Faraday's law, right? If we look at the vector direction of the electric field and the time derivative of a flux that's normal to the surface that is terminated on this loop, we end up with a negative sign in here. But typically, you'll see this written as like VL equals L DIL dt without the negative sign, and that's just because normally, like in a lot of textbooks and classes, we just take the opposite convention from Faraday's law, right? So we say if this is IL, then we say this is positive VL. But by Faraday's law, we would actually say that this is positive VL, right? But anyways, so you can see here that if L is very large, right? If L is very large, then it would take a large voltage just to get a small change in current. And conversely, if L is very large and we wanted to change the current, well, we would only have to change it a little bit to get a very large change in the voltage. So in effect, the inductor is resisting any change in current. If I tried to push more current through it, this voltage VL would become much larger and it would resist that change in current. And if I tried to reduce my current, then the voltage would actually adopt the opposite polarity and try to keep that current going, right? So that's basically two ways to look at both capacitance and inductance.